All right, so we're going to do a quick little mini lecture, and then we'll get started on our inverted work that we need to do today. And so let's start off by talking about di-substituted benzene rings and some of the issues that you might find. And so let's suppose we wanted to make a meta-substituted aniline, and I'm just going to put an isopropyl group out there. What's the problem with that? Say we wanted to make that into benzene. What's the problem that we have?
Both of those are activated.
Pardon?
They like both of those activate the ring, and so
Both of those are activators, and what kind of directors?
ortho-pair.
They are ortho-pair directors, but they are with what? How are they related with respect to one another? Meta. Seems almost impossible to do, except for the fact that we can actually make anilines by reduction of nitro groups. So I can reduce the nitro group to the aniline. Do we have a problem now? I have an electron donating group, which is what kind of a director? Electron. That's an ortho-pair director. That's a what kind of, is that activator or deactivator?
Deactivator.
And it is a
Meta.
meta director. So which group do I need to put on the benzene ring first?
So, deactivator?
Excuse me?
The deactivator?
Yeah, the nitro group, right? The deactivator. So I have to put on the nitro group first. Okay? Because that's going to direct the chemistry. So let's think about this. And we can, of course, get this from nitration of benzene. So we'll just do one more retrosynthesis there to get to the benzene. All right, so what I need to do is start off with benzene. And I'm going to make nitrobenzene. What are the reaction conditions? What reagent do I need? You all used it yesterday in lab. I need HNO3 and what else? Sulfuric acid. That puts on a nitro group, which is a meta-directing deactivator, right? Now what do I need to do? I need to add the isopropyl group. How do I do that? What's the name of the reaction? Friedel-Crafts. So I can do Friedel-Crafts alkylation. So I need isopropyl chloride or something like that. And what else? What other reagent do I need? Say it?
AlCO3.
Aluminum trichloride, right? Are there other reagents that would work there? You bet. I could use isopropanol and sulfuric acid. Anything that gives me that isopropyl carbocation would work just fine. This then puts on the isopropyl group. The ring is deactivated. This might be tough. It might take a long time for this to happen because the nitro group is a strong deactivator. But nonetheless, this is how I have to do it. And now I just simply need to convert the nitro group into an amino group. What reagents would I use for that? Let's start off more simply. What kind of reaction is that? I'm removing oxygens and adding hydrogens. What kind of reaction is that? That's a reduction. What kind of reducing agents have we talked about before?
Sodium borohydride.
We have talked about sodium borohydride. Sodium borohydride is a good reducing agent. It won't work here though.
LAH.
LAH technically will work. It's a bit overkill, but I'd count it on an exam. What else? What about if we wanted to reduce carbon-carbon double bonds? What do we use?
H minus.
Huh?
Can we use H minus? Or no?
That's the hydrides. Hydrogen, And what else?
Water.
What catalyst?
Palladium, metal catalyst.
I need a metal catalyst, something like palladium or platinum or nickel will work here, right? So we can reduce that. There are other reagents that will also do this, okay? A lot less expensive. Palladium's expensive, platinum's expensive, nickel's not too bad, right? You carry them in your pocket. But most of you don't carry platinum and palladium around because it's real expensive. But some cheap metals that we can use are actually iron, and hydrochloric acid will do this, or tin, metal, and hydrochloric acid will do this. Any of those I would take on an exam, but you're going to reduce a nitro group to the amino group. And so what looks like almost impossible to do, because these are both ortho-para directors, right? But we're starting with the meta director, and so we can get the meta substitution that we need, and then convert this functional group into that functional group. Pretty straightforward. The only real problem reaction is this one, in terms of yield, because the nitro group is so deactivating, you might have to let this run a long time, boil it or something like that to get the reaction to go to any appreciable yield. Okay? Any questions about that? Let's take a disubstituted benzene and let's make it a trisubstituted benzene. So let's say we start off with this substituted acid aniline. Okay, and let's say we're going to react this with bromine and iron tribromide. What's the reaction? What are we going to put on the benzene ring? Bromine. We're going to replace one of the hydrogens with a bromine, right? Where's it going to go? Where are we going to put the bromine? What kind of a director is this? That's an ortho-para director. Meaning the bromine can either go here, here, but it can't go there because there's already something there, right? What kind of director is the methyl group? Ortho-para. Which means that the group can either go there, but not there because something's already there, right? So where do we put it? They're both ortho-para directors. Which one's the stronger? That list that we had. Is this stronger or weaker than a methyl group? This one is stronger than the methyl group? You bet. Why? It has the lone pair, right? And so resonance, delocalization into the ring, this is the stronger of the two. So this is strong, this is weak. So where am I going to put the bromine? Next to it, right? And I'm going to end up with my bromine right there. And end up with that product. Okay? So you're going to have to know the relative strengths of your ortho-para directors and your meta directors. You're going to have to know which one's strong, which one's weak. You're going to have to commit that to memory. Okay? Any questions about that before we move on? Let's suppose Megan comes into the laboratory and she wants to put an alkyl group on benzene. Let's say it's an ethyl group. She needs some ethyl benzene for some reason. We don't have it, so she decides to make it using a Friedel-Crafts alkylation reaction. What's the problem with that reaction?
Rearrangement.
I could get rearrangement. Here there is no rearrangement possible. If I had another carbon, that would be an issue. And that is something always to keep in mind. But what's the issue in this particular case?
The stability of the rings?
No, both rings are pretty stable.
Wouldn't that generate a chlorocation that's not as stable, would it like rearrange?
Well, but it can't rearrange anything that's more stable. So we don't really generate a carbocation here, remember? We form the complex and then the benzene ring attacks the carbon and the chlorine leaves.
Is it the solubility?
No, both products are starting material and products are soluble, so it's not a solubility issue.
Would it be because it's an electron donating group?
Ah, and electron donating groups are what?
Ortho pair.
They are ortho pair, but I'm only putting one on. But they're also what?
Activated.
They're also activators, right? So my product, is it more reactive or less reactive than my starting material? More reactive. So what happens once I generate this? It reacts with more of this and over-alkylates. So in reality, Megan, what she's going to find is this is going to be the minor product. She's actually going to get 2 ethyl groups on there, 3 ethyl groups on there, 4 ethyl groups, 5 ethyl groups. She's going to have a whole mixture of products because the products are more reactive than the starting materials. That's a problem. Okay? However, I've told her she still has to make this product by the end of the day and get it in good yield. How can we solve that problem? Put a deactivator on it, right? We can put a deactivator on it. What kind of group is a deactivator that would give me the 2 carbons? Well, but I don't have nitrogen in the product, right?
You just use a carbonyl group.
Ah, I can use a carbonyl group, right? So, what kind of carbonyl group would I use that has 2 carbons in it?
Use a ketone.
Not a ketone yet. It's going to make a ketone.
SC.
But I can use acetyl chloride. Right now, and what reaction am I going to use if I throw in a little aluminum trichloride here? Acylation. This is Friedel-Crafts acylation. And so she runs that reaction. She gets the ketone. This is a deactivator. So what's more reactive, benzene or the product? Benzene. So the benzene reacts and consumes all the starting material, all the reagent, and I end up with this product very nicely. Notice I've got the 2 carbons that I need, right? But I've got a problem. Now I've got to kick off the oxygen. So going from here to here is what kind of reaction? Going from here to here? Reduction. Going the other way is oxidation, right? So we're going to reduce the ketone to the hydrocarbon. 2 ways to do this. Actually, there's more than 2, but only 2 that I really care that you understand about. What might we use to reduce it?
Zinc and mercury with HCl.
Zinc, mercury, that's called an amalgam. Okay, and this is kind of like what they used to put in my fillings for sure, probably none of your fillings. I have zinc mercury amalgam or silver mercury amalgam fillings. So it's kind of like a metal paste stuff that works really well for this kind of thing. And hydrochloric acid, this works. It turns out that you can also not use the mercury, you can just use zinc and HCl. It works really well. You know what the name of this reaction is? I think it's SON, Clemmensen reduction. It may be Ian, I can't remember right off the top of my head. That's the Clemmensen reduction. How else can I do this reaction?
You can reduce it to an alcohol.
I could reduce it to an alcohol. You're getting,
And then take off the alcohol.
I could do that. Technically, I can do that. That's not what I'm thinking about. I could reduce it to the alcohol, eliminate water to the alkene, and then hydrogenate it with H2 and palladium and carbon. That's a lot of steps. There's another way to do this. It's called the Wolff-Tichenor reduction. And it is reacting it with hydrazine and sodium hydroxide under basic conditions. And it will also do the same thing. Why do I need two reactions to do the same thing?
Is one of them stronger than the other? Or is the
That may be. That may be. What is the difference in the conditions?
One's basic and one's.
One is basic and one is acidic. So if I had other groups on here that would react with acid that I didn't want to do, I couldn't use this reaction, right? But I could probably use the Wolff-Kishner because it's under basic conditions. Likewise, if I had something that might react with a base, I wouldn't want to use the Wolff-Kishner, I'd want to use the Clemenson. So you need to have these complementary processes to do this type of work. Okay? Any questions about that? So practically what does this mean? Practically this means that almost always when we're trying to do carbon-carbon bond formation through electrophilic aromatic substitution, we almost always use the Friedel-Crafts acylation reaction. The Friedel-Crafts alkylation reaction is impractical because you have all these other products because the product is more reactive than the starting material and it will overreact. Unless you want to put substitute all the hydrogens for carbon, Friedel-Crafts alkylation reaction is usually not the way to go. One more set of reactions we need to talk about are these alkyl benzenes and things that we can do with those. So let's just pick on the one we just made, ethyl benzene. It turns out that I can convert ethyl benzene into benzoic acid How do I do that?
With KMNO4.
KMNO4. There's a little more, that's good. There's a little more to it though. It's under basic conditions, so sodium hydroxide, and it's hot. You have to heat it up. Okay, and then you follow it up by workup with just a little acid to protonate the carboxylate that you get. Okay? This reaction works great. It's a great way of converting a benzoic carbon atom into a carboxylic acid. If and only if what?
There's nothing else in the group?
Pardon?
There's nothing else on the benzene?
There could be some other things on the benzene ring.
Yeah, Alkyl group isn't starting here.
Getting close. Turns out if this is a T-butyl group, it doesn't work. What's the difference between a T-butyl group on this carbon and this carbon?
Secondary or tertiary?
Yeah, that's the number of hydrogens. You have to have at least one hydrogen on the benzene ring, on the benzoic carbon, excuse me, for this reaction to occur. Okay, so you can have an isopropyl group here, you can have an ethyl group, you can have a methyl group, all those work, but you can't have something like a tert-butyl group. You have to have at least one hydrogen on this benzoic carbon for this oxidation to work. Okay? So you can actually make carboxylic acids pretty conveniently using this chemistry. We've learned how to make carboxylic acids through a couple of other types of reactions. So we're adding to our toolbox here. We can oxidize benzoic carbons to carboxylic acids. What else can we convert to carboxylic acids? What else can we oxidize to a carboxylic acid?
Alcohol.
Alcohol, if it's a what alcohol?
Primary.
Primary alcohols can oxidize to carboxylic acids with Jones reagents. What else can we convert to carboxylic acids? Pardon? Technically, that's correct, and that's along the way of the oxidation of the primary alcohols.
Ester.
We do Grignards with carbon.
Actually, we can convert esters to carboxylic acids through hydrolysis, which we haven't talked about yet, but you're not incorrect.
We do Grignards with carbon dioxide.
We can. You can take a Grignard and react it with carbon dioxide and get a carboxylic acid. What else can we do? Remember when we oxidatively cleaved alkenes and alkynes? Right? We could get carbonyl-containing compounds. We can get carboxylic acids under certain conditions there as well. So the way in which we make carboxylic acids is growing. And one way to do this is to oxidize these benzoic carbons with this hot mixture of potassium permanganate and base. All right. That's all I'm going to talk about today. You all are going to start working on the inverted lecture.